The focus of this section is going to be on graphing rational functions. What is a rational function? A rational function is a function of the form f of x equals p of x divided by q of x, where q of x cannot be 0 and both p of x and q of x are polynomials. So that sounds a little complicated, but this is something we've been doing all semester, talking about polynomials. We just finished several sections in this chapter on polynomials. So what we're looking at here would be a function like f of x equals 2x squared plus 3x plus 1 over x minus 2. That would be a rational function. It could be something like g of x is equal to x minus 2 times x plus 5 over x plus 1. Those are all polynomial functions. We could also have another one, we'll call it h of x here, where we have maybe x plus 3 times 2x minus 1 all over x minus 2 times 3x plus 4. So there's really no limit to how many factors we could have in the numerator or the denominator of our rational functions. Sometimes they'll be presented to us as polynomials that we will then have to factor using our greatest common factor method, our AC method, all the other methods we've looked at before. One thing that is constant here is that we still cannot allow the denominator to equal 0. When we looked at this before in chapter 1, we already got used to saying, but what can x not equal, because what will make us divide by 0? And in this case, we have the same idea. So if we looked at our examples for f of x, we know that x cannot equal 2, because then we would divide by 0. For g of x, x cannot equal negative 1. For h of x, x cannot equal 2, or x cannot equal, let's see, that one would be a little more complicated. Let's see here. 3x equals negative 4. Oh, x equals negative 4/3. So it can't be 4/3. So we did this. We found our restrictions for what x cannot be, right? Our restrictions on our values of x when we were looking at rational functions the first time in chapter 1. So the only focus we're going to really have this time around is we're just going to focus on graphing them, not so much what do they look, what are rational functions? We have seen them before. What we're going to focus on now is how do I graph them? We're going to start our exploration with just the graph of 1 over x. Well, remember from before, this means here that we can't let x equal 0. So x is not allowed to be 0. So what values can x be? Well, let's make a chart. And f of x equals 1 over x. Okay, so when x is 1, f of 1 is 1 over 1, which is 1. So we have the point 1, 1. Okay, when x is negative 1, we get 1 over negative 1, or negative 1. So negative 1, negative 1. Okay, that's not too bad. Now let's try 2 and negative 2. Well, then we would end up with 1/2 and negative 1/2, respectively. So 2 1/2, negative 2, negative 1/2. Okay, let's try 3 and negative 3, 1/3 and negative 1/3. So 3 and 1/3, negative 3 and negative 1/3. Well, let's see what happens when x is between negative 1 and 1, because we're getting an idea of what's happening with the numbers that are getting larger in each direction, whether they're getting more positive or more negative. Let's see what happens between, well, we know x can't be 0, so let's maybe try between 0 and 1 and 0 and negative 1. Let's try 1/2. And this is where we have to remember that 1 divided by 1/2 is the same as 1 times 2 over 1. Keep, switch, flip. or we get 2. So at 1/2, we get 2. Interesting. On negative 1/2, we would get 1 over negative 1/2, which would be 1 times negative 2 over 1, or negative 2. So negative 1/2, negative 2. Okay, let's try 1/3 and negative 1/3. 1 over 1/3 would give us 1 times 3 over 1, or 3. And likewise, 1 over negative 1/3 would give us 1 times negative 3 over 1, or negative 3. So we've got 1/3, 3, and negative 1/3, negative 3. Well, a really interesting picture is starting to grow here. So what happens is we can see here our graph here. These guys are all connected. And it seems like maybe it's going to continue toward this direction. And maybe it's going to continue up toward this direction. It does. Let's see if it does the same thing in the other direction. Well, we've still got these guys. And this one. Notice what it never does, and that is become 0. Remember, x cannot be 0. So what happens then is we have this idea of this line here that x is not allowed to cross. X cannot cross through this line 0 because it's not allowed to be 0. We'll talk about that more in a little bit. But it's not allowed to cross that imaginary line at 0 because it's not allowed to equal 0, or we've broken our function, right? Because you can't divide by 0. Now, for the last part, what would we say would be our domain and range of our rational function 1 over x? Well, this could be an interesting discussion because our domain here does go, in fact, from negative infinity, but it stops at 0 because remember, x cannot be 0, and then it picks up again at 0 and goes on to positive infinity. So our domain would be negative infinity to 0, union 0 to infinity. And the reason why is because we don't have brackets on 0 ever, because we can't include it, because we can't divide by 0. Our range, funny enough, is going to have the same exact values. It's going to go from negative infinity up to 0, and again from 0 to infinity. And that's because there's no value we can plug in for x that would make 1 over x equal 0. We're going to continue our study of rational functions and 1 over x by looking at a new function f of x that is 2 over x plus 1. So if you remember from previous units, what this means is we have a vertical stretch of 2, and we have moved our function to the left one. So we moved left by 1. So that line that we couldn't cross before at the y-axis, which is where x was 0, now moves over to x can't be negative 1. Oh, that's a little hard to see. Let me see here. We'll make it a little bit easier for you to see. There we go. So we have this imaginary line where we're not allowed to let our function equal that number because that's what would cause us to divide by 0. So remember how we did that before? We said that would be where x plus 1 would be 0, which is where, if we subtract 1 from both sides, is negative 1. So x is not allowed to be negative 1. And that's this line right here. X cannot be negative 1. It was x equals 0 in the last one. Now it's called x equals 1. We're going to find out very soon that there's a special name for this kind of line. But for now, we're going to simply leave it as that's the line that says we're not allowed to cross it because that would cause our function to explode. Okay, maybe not literally, but it would mean that we were trying to break the rules of math, which is not a good thing generally speaking. So let's see, if we extend our function from last time to our new function, let's see what would happen. Now we have 2 over x plus 1. So now we have an input of 1. We get 2 over 1 plus 1 is 2 over 2, which is 1. So we still get 1, 1. Interesting. 1, 1 is still on our graph. How about negative 1? Oh, problem, x is not allowed to be negative 1. So here we can still have our 1, but we can't be negative 1. This doesn't exist. It's not allowed. Not allowed. Okay, let's try 2. 2 should work. 2 over 2 plus 1 is going to give us 2 thirds. So we have 2 2/3. Okay, negative 2 will give us 2 over negative 2 plus 1, or 2 over negative 1, which is negative 2. So negative 2, negative 2. Okay, let's see here. 3. 2 over 3 plus 1 is going to give us 2 over 4, or 1/2. So we have 3 and 1/2. Negative 3, however, is going to give us 2 over negative 3 plus 1, which is going to give us 2 over negative 2, or negative 1. So we get negative 3, negative 1. Okay. How about 1/2? Kind of gotten a little afield here. We've got 2 over 1/2 plus 1. Well, that's 3/2. So 2 over 3/2 is 2 times, keep switch flip, 2 times 2/3 or 4/3. That is 1 1/3. So we have 1/2, 1 1/3. So somewhere in there. Okay. Negative 1/2 gives us 2 over negative 1/2 plus 1, or 2 over, well, negative 1/2 plus 1 is just going to give us 1/2. Keep switch flip, 2 times 2 over 1 is 4. So negative 1/2, 1, 2, 3, 4. Well, look at that. That looks slightly different from what we had before. We're going to find out, we're going to add in a different value here in a moment that's going to help us out a little bit too. So instead of doing the 1/3 before we get there, I'd like to instead here, let's do our y-intercept. Since x is allowed to be 0, let's find f of 0 this time, which would be 2 over 0 plus 1, which is 2 over 1, which is just 2. So we have the point 0, 2. Well, we can start to see what the positive side here is going to look like. It's going to go like this. We can guess maybe what the negative side looks like, but we haven't quite gotten there yet. So instead of maybe doing the 1/3, let's go to the negative 1/3. So that would be 2 over negative 1/3 plus 1, which is 2 over 2/3, right? And, well, that's not going to help us much either, is it? That's still going to be in the positive. So maybe we don't do 1/3. How about if we try a different value? Let's try some more negative numbers instead. Let's try, here, we'll just do this, and we'll say, let's try x equals, let's see, we've got negative 2 and negative 3, maybe negative 4. And let's see what happens. F of negative 4 is going to give us 2 over negative 4 plus 1, which is 2 over negative 3. Okay, so negative 4, 1, 2, 3, 4 is negative 2/3. Oh, this is starting to look like what we expected it to. So we can kind of guess this guy's going to go like this. This guy's going to go like that. So does it look like we took our 1 over x and shifted it left and then stretched it? Well, the stretches are going to be harder to see on rational functions a lot of times. But it definitely, we see that shift to the left by 1. That vertical stretch is a little bit harder to find on these ones. What ends up happening is it ends up just usually being more of a curvature in here. and here. We find now that when we just have x instead of x plus 1 here, or the 2 on the top, what ends up happening here without the stretches and shrinks is that if it's stretched, it just pulls this out a little bit flatter than it would if it didn't. Otherwise, we would be here, right? So if we had 1 over x plus 1, for example, this would go through 0, 1. So it would be here. And it would still flatten out eventually, getting close to the x-axis and still getting close to this line at x equals -1 without touching them. But it would just be a little less smoothed out in here. It would be a little closer. And again, for the last part, let's talk about the domain and range here. So our domain now still goes from -infinity, but this time it's going to stop at -1 because x cannot be -1. And it picks up from -1 and goes on to positive infinity. Our range this time still goes from -infinity, right? It still goes from -infinity up to almost 0, but never exactly 0. Picks up at 0 again and goes up to infinity. So we find out here that our range is exactly the same as it was in the last problem. And again, this is because there's no value for x that you can plug in directly that would cause 2 over whatever value plus 1 to be 0. Okay, let's try another one. Now this one is a -2 over x. So this time when we have the negative in the front, we have now reflected, right? Let's see if we remember all of our rules. Now we have reflected, right? This is a reflection over, I hope you remember, the x-axis. And then our 2 is still our vertical stretch. So if we did our same x and y chart, we can see what might happen this time. Let's add in our new function and see where we go. So now we have, let's see if we can fit it in here, -2 over x. So let's figure out what this is. That would mean we would have -2 over 1 when x is 1, or -2. So we have 1, -2. So we can already see it's a little different because now it's in quadrant 4. It's in the bottom right. Well, let's see what happens when we plug in -1. -2 over -1 gives us a +2. -1, +2. Definitely looks like we've made our reflection across the x-axis. Now let's try it with 2. We get -2 over 2. It's going to give us -1. So 2, -1. If we did -2, it's -2 over -2, which any number over itself is 1. Sure looks like we're on the right track. Let's see what about 3. -2 over 3. So 3, -2/3. Okay. Or -2 over -3 is going to give us a +2/3. So -3, +2/3. And if we did 1/2, then -2 over 1/2 is going to be -2 times 2 over 1, keep switch flip, or -4. So 1/2, 1, 2, 3, -4. If I did -1/2, it's -2 over -1/2 is going to be -2 times a -2 over 1, or +4. So -1/2, 1, 2, 3, 4. And even before we look at other values, we can see that all we've done here is take our 1 over x and flip it and stretch it. And again, last thing we'll do is domain and range. So we notice here that we didn't really talk about it, but x cannot be 0 again, which means it can't go through here again. So our domain is now going to go from -infinity to 0, union with 0 to infinity again. And our range is still negative infinity to 0, union with 0 to positive infinity. The only way our range is going to change is if we shift our function up or down. Let's move into one other rational function, and that is 1 over x squared. So unlike the last one where we had negatives and positives, now when we square a positive number, we get a positive number. When we square a negative number, we get a positive number. So this should be all above the x-axis. Everything should be above the x-axis. Let's see what it might look like. Well, here, let's find some values for x and our f of x that equals 1 over x squared. Well, let's talk about first what can x not be. So just as before, if x squared can't be 0, that means x, if we take the square root of both sides, also can't be 0. So we still have this imaginary line at x equals 0 that our graph can't cross or touch. And like I said, we'll find out in a moment that it has a special name. So let's pick some other values since x can't be 0. Let's pick 1 and negative 1, 2 and negative 2, 3 and negative 3, and we'll go from there. So at 1, we get 1 over 1 squared, which is just 1 over 1 and 1. Okay, we can do 1, 1. 1 over negative 1 squared is going to be 1 over positive 1, which is still 1. So negative 1, 1. Okay, let's try 2. 1 over 2 squared is 1 over 4. So 2 is 1/4. Okay, what about negative 2? Well, that's 1 over negative 2 squared, which is still 1 over 4. So negative 2 it's also. Well, isn't this interesting? It looks like we have a function that's symmetric about the x-axis. Well, that makes sense since we have a square. Let's see what happens with 3. If I did 1 over 3 squared, I get 1 over 9. I don't even know if I know how to put that on a graph. We'll just say it's really close down here. And the same thing would happen if we look at 1 over negative 3 squared. It's still going to give us 1 over 9. Interesting. So much like before, let's see what happens when we do 1/2 and negative 1/2. So 1 over 1/2 squared is going to give us 1 divided by 1/2 squared would be 1 over 4. So when we do our keep switch flip, it'll be 1 times 4 over 1 or 4. So we have 1/2, 1, 2, 3, 4. Sorry for my dogs. Yeah, in the same way, we'll have 1 over negative 1/2 squared. We would end up with 1 over 1/4 again, which is still going to be 1 times 4 over 1, which is 4. So at negative 1/2, we also have 4. So this one is a very interesting looking graph because it gets close to that x-axis again, and then it goes up here close to our y-axis. And we find out the same thing is true on the other side of our y-axis. And this is what our squared function looks like. Our 1 over, or should say our 1 over x squared function looks like. And again, the last thing we're going to look at is domain and range. Our domain now goes from negative infinity again to 0, unioned with 0 to infinity. But our range now, there are no y values until we get over 0. And then it goes all the way up to infinity. So our range here is going to go from 0, not including it, just infinitely close to 0, up to positive infinity. So this is a definite difference from the ones we did before. I'd like for you to take a look at this problem. It says f of x is 1 over the quantity x plus 2 that is squared, and then we subtract 1. So I want you to pause, see if you can describe the two translations we have here, and then I want you to try to graph it based on how we graphed 1 over x squared. And then come back and see if you got it right. I'm hoping you said that because this is x plus 2 that we shifted to the left by 2, and because this is a negative 1, we shift down by 1. So we took our imaginary line that was at x equals 0 here, and we shifted it to the left 2 and down 1, which means it's still here at x equals negative 2. So let's start by putting that on our graph. So we have our line here that our function can't cross. That's at x equals negative 2. And if you don't want to do it with translations, you can also say that's where x plus 2 quantity squared equals 0. If we take the square root of both sides, that's x plus 2 equals 0, or x equals negative 2. It's the same thing. It's that vertical line through x equals negative 2. It has a special name, which we're going to find out on the next slide, and we've been using it, but now we're going to know what it looks like. Well, did we do any kind of reflection here? No, we didn't reflect over x or over y, so we still should have this general shape that looks kind of like this. But let's see what happened to it. If we do it even with just x and y values, if we did x and f of x equaling 1 over x plus 2 quantity squared minus 1, and we did some values there. Well, now we can have x equals 0. Well, that's kind of cool. So we have f of 0 is 1 over 0 plus 2 squared minus 1, or 1 over 4 minus 1, so negative 3/4. So we have 0, negative 3/4. Okay. And then we have, let's see here, let's do negative 1. F of negative 1 would be 1 over negative 1 plus 2 squared, and then minus 1. So 1 over, oh, that's just 1. 1 over 1 minus 1 is 1 minus 1, which is 0. So negative 1, 0. Oh, I think I see where we're going with this one. Let's try negative 3. F of negative 3 is going to give us 1 over negative 3 plus 2 squared minus 1, which is 1 over 1, minus 1, which is 0. I see. Hopefully you do too. And then this one would reflect here. And we would find out that we have, let's see here, if we did negative 1.5, let's see here. That would be negative 1.5 is negative 3 halves. So let's see here, f of negative 3 halves. Give us 1 over negative 3 halves plus 2 and square it. So 2 minus 1.5 is 1 half. So 1 over 1 half squared, and then minus 1 is 1 over 1/4 minus 1, which is 4 minus 1, which is 3. That was a lot of work. You can put it in your calculator as well. So negative 3 halves is 1, 2, 3. We'll find out this guy's right here. And what ends up happening is we have our function that looks like, that wasn't so good. Let me try again. You know I'm not the best at drawing, but I do my best here, which I'll keep trying. So we're going up this way. And this guy will also go up this way and come down and around. Oops. There. And as you can tell, yours don't have to be perfect either. So there we are. Something interesting to notice about our graph now is that our domain has changed. So what is our domain this time? Our domain now goes from negative infinity still, but stops at x equals negative 2. So we'll just pick it back up on the other side of -2 and keep on going to infinity. Our range this time has also changed. It now goes from -1 to positive infinity. We shifted it down by 1. It went from 0 before, now we've shifted it down by 1. So again, we have a pretend line here, imaginary line, that it's not supposed to touch or cross. I didn't draw it that great, but it's not supposed to touch or cross there. So what are these imaginary lines that we're not supposed to touch or cross called? They are called asymptotes. Yes, it's a funny name, but that's what they're called. So we have these imaginary boundaries that our curves never touch or cross, and we call them asymptotes. And they work kind of like state lines. If you think about it this way, if this is our state line, and then this side is Maryland, and this side is Delaware, if someone stands right on the border, are they in Maryland or are they in Delaware? Both, but yet neither. So it doesn't really work. So it's this imaginary line, right? No one can actually see the state line. It's not like a literal line on the road or in the trees, right? Or in a forest or across someone's land or house or anything. These are imaginary lines that we can't see. And you have to be on one side of it or the other. You have to be in Maryland or you have to be in Delaware. Your house is not allowed to be in both states. You can't build on a state line. You can't live on a state line. You can't work on a state line. You have to pick either Maryland or Delaware. It works the same if we looked at Maryland and Pennsylvania and we had a person who was standing on that line. It's just that the Maryland Delaware is vertical and Maryland Pennsylvania horizontal. So we would have a vertical asymptote between Maryland and Delaware, and we'd have a horizontal asymptote between Maryland and Pennsylvania. So how do we find them mathematically? This is where things get a bit more interesting because when we look at our definitions here, they seem a little bit intimidating. So formally we say if the value of our function goes to infinity as x gets bigger, then the line x equals a is a vertical asymptote as x goes to this value a. We find this is the important part. We find vertical asymptotes by determining the x values that will cause us to divide by 0. Think back to the other graphs that we've looked at. Each one of those had a vertical asymptote at the value where we divided by 0, and we drew it in as I drew it as a dotted vertical line. Now the other one is saying that if our function's value goes to b as x goes to infinity in either direction, so that's why it says absolute value of x, as x goes to infinity or negative x goes to infinity, or in other words, x goes to negative infinity, then the line y equals b is a horizontal asymptote. So again, what that means is for our function f of x equals p of x over q of x, if if q of x has a higher degree, then there's a horizontal asymptote at y equals 0. If they have the same degree, then the horizontal asymptote is the ratio of the leading coefficients. If p of x has a degree that is exactly 1 more than q of x, then there's something that we call an oblique asymptote, which is a slanted line, and we would just find it through synthetic division. So we're going to look at a couple of rational functions to see if we can determine where they have asymptotes, horizontal, vertical, maybe oblique. Let's see. So our first equation says f of x equals 2x plus 1 over x minus 3. Notice they have the same degree. So this is a degree 1 over degree 1. So we would have a horizontal asymptote at y equals their leading coefficients, 2 over, and since it doesn't say it, 1. So we have a horizontal asymptote at y equals 2. That was easy enough. What about our vertical asymptote? Well, that would be at the point where x minus 3 equals 0. Remember, it's where we can't divide by 0 or where x equals 3. And you're thinking, that's it? And the answer is yes. That's it. That's how we find our asymptotes. Let's talk about the second one here. This f of x says that we have x plus 1 over 2x minus 1 and x plus 3. Now here we have a degree of 1 in the numerator, but we have a degree of more than 1 in the denominator because we have 2x and an x. That would give us an x squared. So we have a higher degree in the denominator. So that tells us that we have a horizontal asymptote at the x-axis, which is y equals 0. We still find our vertical asymptotes in exactly the same way. We would say that would be where 2x minus 1 equals 0 and x plus 3, equals 0. So here we add 1 to both sides, so 2x equals 1. So x is 1/2 would be a vertical asymptote. And x equals negative 3 would be our other vertical asymptote. Make sure you finish the section 3.5 homework before the next exam.